big frame of different pavement design approaches and stuff like that, right. So empirical design, you know, simple to apply, but what to do with the new materials, construction procedures, traffic characteristics and stuff like that. So let's something now. Oh, you have a pointer there. Okay. I can hear there is a kind of. Oh, thank you so much. This is. It is on, I think. I don't know if it works with Mac or not. That's my only problem. Oh, yeah, allow. That should work. Yes. Okay. Several of you said compaction was something that you are comfortable with and stuff like that. So let's visit compaction a little bit for a second. What is the method called when you, the method used to determine moisture density characteristics in the lab? What is the method called? Proctor testing, right? So you know who Proctor, like Proctor was a person, you know that, right? So Proctor was an engineer in California and stuff like that. So he developed this. So you have heard of something called standard Proctor and something called modified Proctor. Why was modified Proctor developed? Heavy loading of compactors, equipment, right? Not vehicles. We're talking about compactors, right? Because the compactors are able to compact a lot better, lot more efficiently, so they needed to do this after World War II and stuff like that. That's why modified Proctor. Does anybody remember off the top of their head the energy difference between standard and modified? 4.5, good. So yeah, close to 4.5. So new construction procedures, new traffic characteristics, new materials. Somebody said, I think here IIT Bhubaneswar or SBNIT, you're working with recycled aggregates or something. Who was that? You said that. Okay. So recycled aggregates, the main difference is going to be their properties, right? So your empirical method most likely is not developed based on that. That is the reason you need to study it, right? So that's new construction materials. You are going to do mixed design differences. You are using now you are using a lot of reclaimed asphalt pavement. I think Dr. Sahu said that India has a 2070 target of net zero or something. Is that correct? Yeah. So now you're talking about a lot of recycled materials, lot of contents, lot of warm mix, lot of cold mix, lot of CIR, FDR. I heard a lot of people say that. So the point is your empirical methods are not designed based on that. That's the reason you're going to do that. Mechanistic design, on the other hand, is all the way on the mechanics side. Okay, but is it achievable? We got into the discussion, but I got distracted. I went into transfer functions. Let's go back to this question. Why is 100% mechanics not achievable? Great point. One, soil is not homogeneous. I like that. Keep going. It's not necessarily visual, right? I know what you're saying, but think about an ideal world when you know exactly how the material behaves. You should be able to predict its cracking. You should be, right? So why can we not do it 100% mechanistic? Soil is not homogeneous is a good answer. Next. That's good, yes. But give me an example. I mean, yes, that's the whole story. Yes. Okay. So you are saying your analysis approaches are assuming certain boundary conditions or something we don't expect, right? Correct. That's number 2. What else? There's a lot more. You can keep going. Whose fault is that? Whose fault is that? That's not an excuse, right? I mean, then we need to be better at mathematics then, right, or physics. Okay. So now he's talking about climatic effects. Okay. So, but let's think about this. Climatic effects, if we have really good thermodynamics models and climate models, shouldn't that be taken care of? If that's the reason, right? I am talking about, let's just say we get all the physicists in the best in the world together in a room saying that solve this damn problem, right? Why can't they still do it, is the question. Okay, so practicality meaning you are saying that an engineer may not be able to solve that and stuff. I mean, apply that all the time. Is that what you're saying?
The suggested solution may not be applicable as engineer's point of view.
Yeah, that's what. So okay, so that, but again, that's a valid point. It may not be practical. I am saying it is not impossible. It's not possible. I'm saying, so there is a difference between practical and possible, right? I am saying it's not even possible to do this, mechanistic. Practicality, I totally agree with you, but I don't think that answers my possibility question. How many of you have seen a road being constructed? You have, okay? Can you guarantee that the soil the compactor is working the exact same way at every position? Is the being exactly the same and stuff like that? Can you guarantee that the mix that you tested in your IIT Bhubaneswar lab is the exact same that's being put in the road and stuff? Do you know? So those of you who have worked on mix designs, asphalt mix designs and stuff, there is something called, you know, the target mix design, and there is something called the job mix formula. I don't know what the term is used in India, unfortunately, but the actual formula that actually goes in the plant is actually different from what you are constructing. So you build all your models for something, the road is constructed with completely different material, right? That's the reason it's not possible. You don't have the answer, right? You are trying to do a 3-point or a 4-point bending test, saying this many kilonewtons acting at 50 hertz, blah 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 and stuff. Now you are having an entire traffic spectra in the road, right? Traffic spectra is completely different, right? So we have so many unknowns that it's not possible for us to do that. That is the reason mechanistic design is not possible, right? We just don't have all the inputs. Those of you who have done Ashto Road 1993 or something, you know there is a reliability factor in there, right? Right? You know why the reliability came into picture? The reliability actually came into picture by saying that they targeted some kind of a testing in the lab and under controlled conditions and stuff, and they actually went and measured those conditions in the field, and the difference between those two is actually the reliability, the S0 square that you see and stuff like that, right? So mechanistic is just is a white elephant. It doesn't exist. Okay, the best we can do is ME, right? We have to go as far as we can with our mathematics, and then we use, and then magic happens, and then cracking, right? That's basically what it is. So if you go into MEPDG or pavement mechanistic empirical design, there is something called global calibration, there is something called local calibration. That's what this is. Why are all these states suffering to do this? Is because not everybody has been able to do successful local calibration. Okay? Okay, how many of you know anything at all? I mean, okay, I think that's a bad question. How many of you have some exposure to asphalt mix design? sum. Okay, that's not a big enough number for me to do. So let me just do this. Mix design approach keeps changing with time. Okay, there's something called volumetric mix design, which was called the super pave and stuff like that, which is VMA, VFA, blah blah blah, all of that stuff. Now there is something called balanced mix design or performance based mix design or something like that. I'm not going to go into all the details because not everybody is asphalt person here, but the point is you are changing your material input significantly as well, right? Let's just say I am a state DOT and I invested several $1 million today and over the next 5 years to establish my local calibration factors, and I'm like, bam, I got it. Next day my materials engineer says, hey, I'm going to adopt balanced mix design, I'm moving away from super pave. What does that do to my local calibration? It all goes down the drain and stuff, right? It's very difficult. It's not that easy to do this, right? So that is the reason. It's not that, you know, scientists are dumb or people have not paid enough attention. It is just that it's a moving target. It's a very moving target. That's the reason. Typical pavement structures, again, most of you will know this. We are going to focus on base, sub-base, compacted or natural subgradient, embankment, natural soil and stuff like that, right? Everything below the surface layers and stuff. Or starting from the surface layers, you know, if you're talking about unsurfaced roads or gravel roads or something like that, right? So just a typical thing. Stress distribution. Okay, I think everybody should know this. There's a very little thing. This is for the new master students and new PhD students who are getting ready for their qualifier exam. Do you guys have a qualifier here or something? Is that a research proposal or is it like a knowledge test and stuff? Knowledge test. Okay, good. So that's what I was talking about. So if you're getting ready for that, people actually start saying things like, and this is something I see all the time, I hope a lot of you realize, people say that as we go down in the layer, the force decreases. Is that a correct statement? Stress decreases. Force does not decrease. If force decreases, then the thing will be flying out, right? Force equilibrium has to hold, right? So don't let Newton turn in his grave or something, you know. Be careful about statements like that. So there is stress distribution changes, force distribution does not change, right? Similarly, things like, you know, we will get to this on day 3 and stuff. People say things like, I have a very high resilient modulus, or I have a very high modulus thing. So this is a very strong layer, right? No, it's not. It may be a stiff layer, right? Strong represents strength. Modulus has nothing to do with strength, right? So pay attention to mechanics, pay attention to physics, right? Modulus is a slope of the stress and strain curve. Strength is the maximum stress value that the material can take. Do not make them the same. So a gravel layer, yes, it may be stronger because you just got lucky that the shear strength is also higher. But don't say that a higher modulus means that it is stronger. Say higher modulus means it's stiffer, right? But then there is a difference between what is stiffness versus what is strength. Sorry, what is stiffness versus what is modulus. Let's do that right now, actually. This is a good time. What is stiffness? Resistance to deformation. Right answer. Give me the mathematics. And you don't say. You finished your PhD. Others. K is equal to F over delta, or delta. Yeah, K is equal to F over delta, right? Or F is equal to Ku, which is the fundamental of what? Spring and the entire finite element method. Those of you who have studied it, right? Stiffness matrix is basically what it is, right? What is modulus? Wait, no. What is the unit of stiffness then? What's your name next to Chanchal? What's your name? Raki. Raki, what's the unit of stiffness? F over delta. What's the unit? Meter. Newton per meter. Good. Now let's talk about modulus. What is modulus? Stress over strain. Young's modulus, basically modulus, stress over strain. What is the unit of stress? Pascal is Newton per meter square. And what is the unit of strain? Unitless. So what is the unit of modulus? Newton per meter square. And what is the unit of stiffness? Are they the same? No. Case closed, right? Stiffness is not equal to modulus. The problem with us pavement engineers is we always try to talk about them as the same language. You need to remember this. You know why you need to remember this? Because we actually encountered this in Tanmoy's research. He was trying to design some springs for his mold to support and stuff, and he had a stiffness. And I said to model it in Abacus, which is a finite element based software, where the layer is assigned a modulus. You can't equate them directly, right? That's going to be useful because we are going to look into all of that. When you do a design of a pavement, flexible pavement, modulus is a very important component. It's called elastic modulus. We'll get into resilient modulus. Rigid pavements, again, here researchers, what is the unit? What is the equivalent input? Not modulus, something else. What is it? It's not resilient modulus. Modulus of subgrade reaction. Do you remember what that is? Do you remember the unit of that? Meter per meter cube. Now we are throwing another meter in there, right? We must be something seriously wrong with us, right? So you have to understand in your subgrade evaluation what you are studying and where values are coming from, and then you are going to be able to compare things and stuff, right? So we'll take a look at that. So surface loading, you know, in the pavement, as you go down, the material quality decreases, right? Lowest material at the top and the highest material at the lowest material at the bottom, highest material at the top, because that's where the highest stresses are, not highest loads are. 90% of master students or initial PhD students will say the loads are greater at the top. The answer is no, loads are same everywhere, otherwise your system is going to be fly, right? So very strong, durable, impermeable, manufactured, expensive. Strong, free draining, manufactured, less expensive. Okay, there was in transportation geotechniques or in general geotechnical engineering, if somebody tells you what is your biggest enemy, right? Water, right? So there was a very famous scientist called Sedergreen. He wrote a lot of books on drainage and stuff like that. His famous saying is that a pavement engineer needs to worry about only one thing: water, water, and water, right? So drainage, free draining. Let's talk about railroads. Some people actually asked some questions about railroads and stuff in their homework 0 and stuff like that. You know what a ballast layer is? The rock layer. That's called ballast, right? Do you know what is the primary function of a ballast layer? Drainage. It's not load transformation. It is, I mean, it does transfer load, but the primary requirement for selection of a material is drainage. Because if water doesn't drain, what happens? Swelling is very soil dependent. It may not swell. Maybe, yeah, in black soils, yes, I would agree. What happens when water cannot drain? What happens under loading? Pore water pressure develops. Higher the pore water pressure, what happens? Lower the effective stress. And what governs your shear strength? effective stress. So what happens? Your shear strength collapses, right? So water is very important. We need to be careful about that. Then comes the question again in day 3. These are all open ended. I mean, this today is all about introduction anyway. The point is, we're going to talk about this, is when you do a resilient modulus testing on an aggregate layer, should you be worried about a drained condition or an undrained condition? Why? Right answer, but why? It should not accumulate water. Base layers are designed to drain water, right? So it's a drain test and stuff. Well, I should not say drain test, because drain test means it's a very long. It's actually an undrained test, because you don't worry about the thing. We'll worry about that later. Subgrade, always I prefer this. Again, your courses may be different. I always prefer to divide subgrade into 2 parts. One is called the natural, that I don't touch, and one is called the prepared subgrade or compacted subgrade. Because when you are building a road or something, you're only compacting about 2 feet, 24 inches maximum, maybe 36 inches, not more than that. Below that, the world still exists, the earth still exists, right? So always divide that into 2 parts. Why worry about subsurface layers? Nearly all the measures of pavement performance are based upon observations at the surface of the pavement, right? We are riding on the roadway, we are seeing the effect on the roadway, which is rutting, which is cracking, which is ride quality, right? But if you go back to the Ashow road test, the percent of total surface rutting, if they divided it, they said asphalt layer was 32%, granular base was 18%, sub base was 39%, subgrade was 11%. So 1139 is 50 plus 18 is 68%. 68% of the rutting was actually coming from the subsurface layers. That's why transportation geotechnics is important. Now I will tell you one thing, it is possible to kind of mask over this problem sometimes by building a very thick concrete slab or doing a really big, cement stabilization of a base or something and then build an asphalt. It's possible to sometimes overcome this. But then the problem is, are you doing your job as the engineer to do the most economical, sustainable, resource efficient design? The answer is no, right? So that's the reason you need to look into that. Okay, geotechnical influences on flexible pavement distresses. Let's take a look at this. So fatigue cracking, also known as alligator cracking, right? Because the cracks look like alligator skins, stuff, right? Insufficient base stiffness or strength, yes. Insufficient subgrade stiffness or strength, yes. Moisture drainage problems, yes. Freeze thaw conditions, yes. Swelling does not do fatigue, because fatigue is a repeated application, right? Swelling probably happens once. Swelling can do shoving, swelling can do other things, but not really bumps and stuff, but not that. Contamination, erosion, no. Spatial variability, not really. Rutting, again, weak layers, moisture damage, freeze thaw. Okay, by the way, how many types of rutting are you familiar with? 2 types. What are they called? Say it again? Yeah, I mean, yes. So it's called primary rutting and secondary rutting, right? Primary rutting is what happens inside your asphalt layer. Secondary rutting is actually it's going underneath. Primary rutting means your mix designer did not do a good job, or your asphalt compactor did not do a good job and stuff. Secondary rutting is you're going deeper, right? So that's what we are going to worry about primarily, right? Corrugations, again, because thin layers and stuff that can actually sometimes make lead to these undulations and stuff. Bumps, freeze thaw, swelling, spatial variability, depressions, potholes, roughness, all of that and stuff like that. So all the aspects that you see are going to be because of, I mean, all the distresses you notice somehow can be affected by geotechnical layers and stuff like that. So you just have to be careful when constructing, because if you have a problematic, you know, infected wound or something, no matter how many band-aids you put over it, it's not going to be fixed. You need to cure it, right? So there is no other cure. Rigid pavements, okay, fatigue, punch outs, which is seen on continuously reinforced concrete pavements. Pumping is a big erosion issue. Faulting, which is the elevation difference between the slabs and stuff. Roughness and whatnot, all of that. So if you see here, even in the rigid pavement, moisture and erosion are basically the two that have all excess. If you go into the subgrade strength, see how it doesn't have all excess? That's because several of rigid pavement distresses you can get by with weak subgrade. It's because the slab carries most of the load, right? It's not as demanding on the subsurface layers and stuff like that. This is on rehabilitated pavements, AC over PCC, mostly reflection cracking and roughness and stuff like that. So this is just some information. Some terms that you should be familiar with. Okay, optimum moisture content, maximum dry density, you know that, right? Everybody knows that. Triaxial testing. Okay, let's talk again. This is just laying the foundation for the future stuff, right? So you have learned about when you talk about triaxial testing, you draw more circles, right? So if you want to draw more circles, you have, who remembers what's the x-axis? Stress. Principal stress. Normal stress. What's the y-axis? Tau, right? And then you do this, and Rakhi just said this is sigma 3, sigma 1, sigma 3 prime, sigma 1 prime, like other case and stuff like that. That's what you just said, right? So these are called principal stresses, right? What's the definition of a principal stress? On what? On a principal plane. So what is the principal stress? The principal stress is the normal stress acting on the plane on which shear is 0. Why can we plot a cylindrical triaxial data using more circles? The loads that you are applying on a cylindrical triaxial test, right? So this, you call this what? Sigma 3, you call this sigma 1 and stuff like that. We'll get into all of that details and stuff, right? Why? Why do we write sigma 3 and sigma 1? Why do we by default say that these are principal stresses? Have you thought about it? You know sigma 3, right? Confining pressure. Why is the confining pressure not just a normal stress? Why is it principal stress? Normal stress is perpendicular to the surface, right? There is no shear on that plane. So in a cylindrical triaxial testing setup that you are applying, you are not applying any shear on those planes. And what law is that? What are you using for confining the devices you have here? Is it air or is it water or is it oil? What do you have? Water, some water, mostly water, probably air or something. What law was it? That Pascal's law, that any point the stresses are normal in all directions. That is the reason the stresses are normal here. That is the reason there is no shear stress. That is the reason you can plot it using Morse circles, right, because that by default becomes the principal stresses, right. And because you are doing cylindrical sample, your intermediate and minor principal stresses basically become the 1. 2 does not exist, it is the same as sigma 3, right. So that is what you are talking about. Okay, shear strength, we already talked a little bit about this, right. It is the maximum stress that the material can undertake, right. So then you will go into these things called Mohr Coulomb envelopes. We will get into all of that. You will draw this, and you are like, okay, there is no point that's above this, and stuff like that, and whatnot, and whatnot. So we can talk about that, those things, right. Then modulus versus stiffness, we went a little bit that. I don't think in this class, in this course, I'm going to go into PG grading of asphalt much, but that's the performance grade, which is a way of defining asphalt like quality and stuff. And then pavement distresses, you know this, you know this. So because we are going into mechanistic empirical and discussing all of that, what are the primary responses that we care about? What are the responses, the critical pavement response parameters? Do you remember those? Horizontal, tensile, what did you say? Strain. Okay, so epsilon T, where? Bottom of the asphalt layer. Okay, good. So we have this, let's just do this. We have a HMA, we're doing a base, we're doing a subgrade. So you're saying this. Then vertical strain. Okay, where? Right here? Subgrade. Okay, sure. What else? What else? Tensile stress and strain where? Top of the subgrade? Good point actually. Can subgrade take tensile tension? Can it be? What is the base nature? Base is a unbound layer. Can an unbound layer take tension? Yes, yes, for sure. But that's actually a very good point she just raised. How many of you have run a what's it called? It's called IIT PAVE here, right? IIT is IIT PAVE finite element or layered elastic? Layered elastic. So have you run IIT PAVE? I can guarantee that if you run it, you will see tensile strain in the base layer. That is a manifestation of layered elastic analysis theory. That is the reason when we go into ILI-PAVE and stuff like that, the finite element, we will go and we will say that the moment it goes into tension, cut it, redistribute, because tension is not possible. I am glad you brought that point, because yes, theory gives you that, practical is not possible, right. So we have to know the difference between the two, right. So okay, by the way, this is correct, epsilon v, okay, but there is actually some modern, not modern anymore, there has been research that actually shows that compared to epsilon v, it is actually sigma v on top of the subgrade that is more important than epsilon v, the stress, because there is something called subgrade stress ratio. We will go into that tomorrow. How does the stress compare to strength? QU, unconfined compressive strength, you know that, right? So where are you with respect to that? How does that ratio affect your behavior? We'll get to that tomorrow during subgrade evaluation and stuff like that. So SSR is a very important concept, Okay. So these are the critical pavement response parameters that you should be interested in. So anytime you have to build a, you're analyzing a pavement or something, you're going to pick these, and then what? These are used to predict. What are these, by the way? Response or performance? Response. So what are they used to predict? Performance. That's where the transfer function comes into picture, right? So you're going to pick these, and then we are going to predict how this is going to lead to alligator cracking or fatigue cracking, subgrade rutting. That is actually another one that gets measured here, is actually the deflection at the surface, delta at the surface, right? Because we are getting into all this discussion, let me ask you another question here. What kind of a phenomenon is rutting? Vertical deformation, that's correct. Elastic or plastic? Plastic? Yes. What kind of analysis is any layered elastic analysis, like IIT PAVE, Ken layer, all of that? So we are doing an elastic analysis to predict plastic deformation, right? As long as we know our limitations, right? We are doing an elastic analysis and predicting plastic deformations. Just know that. I am not saying that. Why? Because doing plastic modeling is extremely difficult. It is prohibitively difficult. That's where the practicality issue comes into picture and stuff. We are not going to be able to do that. But we need to remember there are differences. We need to worry about those things. Can we relate the response and performance in FEM modeling? Again, it is all dependent on how good of a hand material. If you are saying, can I use FEM to predict crack propagation? Yes, you can do that. You can do that. But again, what is FEM? It's a continuum model, right? The moment there is a proper cap, proper crack, continuum falls apart, right? That's where you have to go into discrete models and stuff. That's very different, right? Which is called discrete element and stuff like that. Okay, I posted this for you all yesterday. You should have downloaded this already. Please keep this in your archives. It's it's a very good read. You'll enjoy this. Okay. I think you know this. Several types of flexible payment. This is just background stuff. I don't think we need to go over this anymore. Conventional, deep strength, full depth. Okay, how many of you have heard of the term called perpetual pavement? What is a perpetual pavement? That's it? Now you're throwing complicated stuff at me. Okay, perpetual pavement it's perpetual. It's like Pitama Bhishma, it doesn't die, right? It can go into what is known as the Sarasarja or something, it will not die, right? How does a pavement die? Fatigue cracking, rutting, right? Fatigue cracking, yeah, there is something called top-down fatigue as well, but mostly traditional physics says it is bottom-up. So now you have a good enough layer that is bottom, it's rich at the bottom, so the strains are, even if it's big strain, because it's rich, the modulus is low, it doesn't crack anymore. And the rutting is you have a rut resistant layer. So all you need to do is a perpetual pavement is just do some milling and stuff, just some surface maintenance and stuff, it will stay, right? So the point is, in a perpetual pavement you never ever get to the subgrade layer or the base layer, because that beats the purpose and stuff. So there you have to have a proper design before you start building. A lot of times you do a lime stabilization of the subgrade, which you do like a full depth asphalt and stuff like that. This is just, again, background information for you all to keep on top of things. Rigid pavements, JPCP, jointed plain concrete pavement, reinforced concrete pavement, CRCP, PCP and stuff like that. Again, as I said, rigid, it's a little bit forgiving, more forgiving for your mistakes on the underlying layer stuff. Erosion is a big issue, pumping is a big issue, strength you can get by. Unevenness is a big issue. If you have really varying properties, that causes a lot of problems. And then curling and stuff becomes big. It's composite pavements, major material types. Again, this is just background information for you to keep. I hope everybody is kind of familiar with the basic definitions of soils and stuff, the classification, how it works and stuff. What does plasticity mean? What is high plastic versus low plastic and stuff like that. That's something we're going to use. Soil classification, density, water content, stiffness or strength, resilient modulus, modulus of subgrade reaction, thermohydraulic properties, drainage coefficient, permeability coefficient of thermal expansion, performance related properties, which is repeated load, permanent deformation characteristics and stuff like that. What are special challenges? You have expansive soils. That's India, a lot about it already, right? Frost susceptible soils, materials, right? Freeze conditions. What is the primary requirement for freeze thaw to happen? Say again? Water, one. Water, okay, let's just call it water. Second, low temperature, otherwise it's not going to freeze, right? Third, water, crack leads to water, yes. Third, say again? Air voids, how? It is lower than what? Are you talking about the asphalt layer? I don't understand how it is. Oh, no. Oh, so you're talking about the ability to capture freeze thaw stresses. That's a different thing. I'm talking when will freezing happen. Yes, you are right. If there is air voids, there is a cushioning effect, the shock absorber basically, like you can absorb some shock. You're right. But I'm not talking about that. I'm talking when is frost a problem? Frost heave is a problem. Water, low temperature, and the other is the layer should have enough permeability for water to be moving through it and have that kind of a problem, right? The interesting problem, the freeze thaw and frost susceptibility and all of that is not as big of a problem on clays. It's actually a bigger problem on silts. You know why? Because clay has such low permeability that water actually does not even move far enough for you to have that problem. Silt has just the right combination, little bit higher permeability that water can move and it is still frost susceptible and stuff like that, right? So frost susceptibility matters. I mean, I don't think frost is a problem in Odisha, right? We barely get below, what, 15 degrees Celsius or something maybe, right? Karst topography, pumping soils, highly fluctuating groundwater conditions, like these are all things that are going to affect your soils and stuff. Already said that. Collapsible soils, again, metastable structures, large volume decrease when saturated and stuff. So this is all problems. This is actually an interesting plot from actually from AASHTO 1993 analysis. This is subgrade CBR, required base thickness. Okay, so AASHTO 1993. If you don't remember that, maybe you should review. You put a subgrade stiffness and you basically calculate the structural number required to protect the subgrade, right? We're talking about philosophy here, right? The entire philosophy there, folks, was what? Protect the weakest layer. That is AASHTO 1993. You just protect the weakest layer. There is no focus on what happens within the asphalt layer, what happens within, like any cracking happens in there or something. There is no such thing. It is basically protect the weakest layer, right? So subgrade CBR, as the subgrade CBR increases, your required base thickness decreases significantly, right? But this is base percentage of overall structural capacity. So when the subgrade CBR is very high, your base does not have to take a lot of structural capacity. Your subgrade is also contributing, right? Like when you have that sibling who doesn't make a single penny, you have to make most of the money to support the house, right? That's basically what it is, right? When both are supporting equally, not the entire load is not on one person. Base CBR required AC thickness. Remember, see, as the base CBR increases, AC thickness goes down significantly, and also the contribution from the base layer actually goes. And the base overall structural capacity can go up to 50%, folks, for a pavement, right? So up to 50% of the structural capacity comes from the base layer itself, right? That's why I said in flexible pavements, substructures play a much bigger role than rigid pavements and stuff like that. Drainage, 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 right? Huge issue. That's why you go into, like, there are big fields. There is fields on, you know, how do you construct edge drains? What are the wicking geotextile applications and stuff that will actually remove water and stuff, because there is a lot of this actually is a, oh, this is by McAdams. See, the roads can never be rendered thus perfectly secure until the following principles be fully understood, admitted, and acted upon, namely that it is the native soil which really supports the weight of traffic, that while it is preserved in a dry state, it will carry any weight without sinking, and does not in fact carry the blah blah blah, and that thickness of a road should only be regulated by the quantity of material necessary to form such impervious covering, and never by any reference to its own power of carrying the weight. That was the underlying philosophy. You know, actually in India the word macadam is still used, right? I think it's WBM, WMM and stuff like that, you still use that, right? That's the engineer, right? That's the UK engineer, Macadam. He actually developed all of these things, right? The erroneous option so long acted upon and so tenaciously that placing a large quantity of stone under the roads, a remedy will be found for sinking into wet clay or other soils. In other words, that a road may be made sufficiently strong artificially to carry heavy carriages, though the subsoil be in a wet state, and by such means to avert the inconvenience of natural soil receiving, has produced most of the defects in the roads of Great Britain. Essentially, if you think you can put enough band-aids to cure an infection, you're going to die. That's basically what it is saying, right? You have to fix the underlying problem. Macadam, 1820s, we're in 2024. 204 years, we still haven't solved the damn problem, right? That's the thing. Sources of water, seepage from high ground, vapor movements, capillary action, rising water table. These are all things that you will have to be careful about as engineers. How do we control, reduce moisture, prevent moisture, use material design features that are sensitive, insensitive, and quickly remove moisture that enters the pavement system? So all of these things are again part of transportation geotechniques, right? You have to design drainage, you have to worry about freeze thaw, you have to worry about frost heaves and stuff like that when there is things. Structural failure, functional failure, again just introduction for today, so that we can get into all the details tomorrow and onwards, so that we don't have to cover anything. Significant load related versus environment related, right? Environment related is something we really have to worry about too, because it does affect right? Asphalt, you'll just have thermal cracking. If you don't do anything, low load, still have thermal cracking or block cracking and stuff. Failure can be functional failure or structural failure. This is something we already discussed today. In functional, people always worry about ride quality and cracking and rotting, all of that. We do not have good enough models to talk about surface friction. Surface friction is another very, very important component of functional. We assume that it's going to be taken care of by our materials. We're going to have good enough aggregates that are polish resistant, that are going to provide the friction and stuff. That's why you do the friction testing and all of that stuff, right? But that's another very, very big functional thing. Present serviceability index stuff, just performance curves. Don't think we're going to use that much in this class. I'm sure you have seen this. With time, there is some form of drop, and this is where maintenance comes into picture. Like at what point you do the maintenance so that you optimize the schedule rather than spending a lot of money. I think this is the last slide on this block, but the whole idea here is I stand by what I said. If you are doing an empirical design or empirical method and you are still within this circle, you are still okay. The problem happens when you do these. You have no idea how the material or how the system is going to behave as the load increases, as the number of freeze-thaw cycles increases, as the number of rainy days increases, as time increases, just oxidation of the layers happens and stuff like that. You don't know any of that. That's when the problem is. Extrapolation. How many of you have taken a linear regression class in your life? Some kind of statistics class, right? I'm sure your linear regression professor also told you that regression, do not just blindly extrapolate. Extrapolation is danger. Regression works in the area that you're talking about, in the domain that your data was developed for. That's basically what this is. Last thing for this block, railroad track, right? I told you this. Close your eyes and imagine this did not exist. This was just an asphalt layer or something. Underneath that, it's the same thing. There's no difference. Same concepts apply. Same layered elastic theory. Same properties. Same subgrade evaluation. Same shakedown. All of that happens. There are some challenges. There are some other things. One of the biggest challenges is railroad ballast is very, very open graded. And open graded materials are extremely difficult to work with. If you want an example, you know, marbles that kids play with, marbles, if you put it in a mold, Proctor mold, and do a hammer on this side, the material just raise here. You bump it here, it just raise here. That's what railroad ballast is. It doesn't compact. So you have to vibrate it to the optimum configuration and stuff like that. That's the primary. Otherwise, pretty straightforward stuff. There is a phenomenon called ballast fouling. Okay, it's called ballast fouling. F-O-U-L-I-N-G. Fouling. It basically means it getting dirty. Okay, and ballast fouling can happen because of many reasons. The ballast itself can break down because it's a very open graded material, right? It can break down, voids will be filled, or subgrade may pump, or you're transporting coal and coal may spill. All of that can lead to ballast fouling. Okay, ballast fouling is a very bad phenomenon. Okay, but one thing you really need to understand is, if you have a fouled ballast in the middle of a desert, right, it's dry, the shear strength of that ballast, or sometimes the modulus, may actually be better than an open graded ballast, because now the fines are stabilizing the matrix a little bit and the system is actually more like a well graded system than an open graded system. The problem happens when it rains, hence water is another thing. When it rains, there is a lot of lubrication happens at the ballast, and then the thing starts falling apart. And also, if it rains and if it is fouled, then water cannot escape. If water cannot escape, under dynamic loading there is excess pore water pressure. With excess pore water pressure, you have reduced effective stress. All of that happens, right? So that's basically what this is. Okay, so that was this block. I think again, reminder, those of you who haven't sent this, please send it in today. Before tomorrow, I want these things. We're going to break at 1, right? Yeah, I think I'll take a 5-minute break. And then we can probably go a little bit more and then break for lunch or something. So that's, yeah, let's take a 10 minutes break, folks, and then I need to drink some water. And then we'll finish the last thing. We don't have very long, maybe 20 more minutes, and then we'll break for lunch. Okay? All right, thanks. I think we'll go more than 15 more minutes, 15, 20 more minutes, and that will be, and then we'll break for lunch and then tutorial. So we covered good ground today. Here is what you're going to have for tomorrow. This is a paper I'm going to send most likely during lunch. It's only a 5-page paper, it's a very short paper. Please read this before coming tomorrow. It's by one of my former professors. This is a very old paper, sometime in the mid-90s and stuff like that, but it's a very, very relevant paper about what is the overview, what should we watch out for, what is mechanistic empirical, and what's the framework and stuff like that. And this is written for a pavement design point of view. The same thing holds for railroads. It's exactly the same, right? What needs to be watched out for and what needs to be done. We have had a lot of discussions. So I'm going to do this Menti for you guys right now. So pull up your phones. Give me a few. This is a word-based question. So give me a few disadvantages of empirical pavement design approaches. It's typing based, so just type it up. Complicated to understand. Based on past experience, doesn't consider actual payment responses. Okay. Projection directly for other conditions. Okay. Oh, one was hidden over there. Hold on, I need to change something here. Change my Menti slide. Keep going, it's not going to affect your thing. Oh. This is the problem. I can't even find my there. There, swap displays. No. Escape. Design, show QR code, boom, there. Okay. Cannot be generalized for different traffic, climate, and material conditions, implemented for specific area or material specific, too much mathematics. Actually, it's not, because we're talking about empirical. So it's mostly based on performance curves and stuff like that. So trends. So that is actually not correct. Might not be valid for all places. Wide range of traffic. Where are the others? How do I see all the others? Is it scroll? I'm relatively new to this Menti thing, so I'm trying to figure out myself. That's over there. I don't know why it is doing this. Oh, okay, it's a big scroll. Okay, let me do this. I'm going to connect this. And we're going to drag this over there. And then we can scroll this right now. Okay, valid only for limited geographic and environmental conditions, limited applicability flexibility based on experiments, so not completely realistic for future conditions. Playing all sorts of same empirical design would not work for different locations. Region where past data is not available, limited applicability, does not consider climatic variabilities. This I don't know. I mean, if you have data across other climate stuff, probably valid, right? So you may be able to handle some of them. Again, this is just an discussion, folks. Based on experiment, not completely realistic, does not for future conditions. Okay, yes, does not cover large field, change in traffic pattern, limited geographical, yes, based on past experience, blah blah blah, may be applicable. In we're not considering. Okay, I think most of you got the gist of it. I think except for that mathematics thing, which I don't necessarily agree, I think all of that is probably correct. So I think I'm going to try to summarize this and send it to you all. That way you have it, what the entire class thought. So yeah, it's just a refresher of things. The question is it all bad? It's actually based on actual data, which is a good thing, right? It can be reasonable if used in the data range, and sometimes it's faster to rely on experience than to investigate the cause and stuff, right? So what I'm trying to say is, yes, I mean, from a pavement design perspective, we all agree. I mean, there is no, I'm not saying empirical ways, but what I'm trying to say is, give this deeper thought when talking about empirical as well. Sometimes in some scenarios it may be good. Let's just think about a special case. Let's just say that the state of Odisha comes across a very special recycled aggregate, a waste aggregate that can be used here. It's not commonplace in the rest of India, rest of world or something like that. They don't have to worry about developing general performance equations for it and stuff like that. They would just test it here, develop some kind of a performance curve, and then just use it in the. It's perfectly fine, right? There's nothing wrong with it. You just have to give that a little consideration. But yes, we all agree on that. Mechanistic solutions to all problems, is that correct? You know, Buzinesque started this, the single layer point load application and stuff. Then Burmeister went into this and said it's going to be multi-layered and stuff. He started with 2 layer, then he later wrote a 3 layer, and then he then that was extended to n layers. There is differences in the friction between the layers and stuff like that. In India, there has been a lot of very high work that has been done by in this field. I mean, who was Animesh Das's advisor? Dr. Reddy? Pandey, B.B. Pandey, right? Yeah, so he did a lot of work. Animesh Das, Dr. Animesh Das from IIT Kanpur, his work is a lot on this. His book actually goes into a lot of this theory and stuff like that. I actually use his book quite a bit. So in India, there has been a lot of work as well, but it is all again layered elastic analysis and stuff, and then Westergaard on the concrete side, slab on grade and curling theories and stuff like that. The concept of dense liquid foundation and stuff. I don't know some of you know this or not. Winkler foundation and stuff. Do truly mechanistic design methods exist? Right. So based on that, again, this is another one. Let's try to do this. I am really having trouble with my cursor in this computer. Okay, there it is. Hold on for a second, there's something wrong here. Info, reload. It's not giving me the option to start it. I need to figure out tomorrow. There it is. Okay, let's go. Oh, I need to again remove that thing. I hope I can figure this out. Let's start from here. We'll go one by one. Based on many assumptions, 100% dependency because there is some human errors. I am hoping you're talking about human errors in construction and stuff like that, not the mathematics necessarily. Replicate in the same conditions, performance can't be determined. See, again, this is not something I necessarily agree with, because if you have really good models, then you may be able to predict from response to performance as well. That mapping may be possible as well. But yes, mostly that's practical. Not homogeneous, quality control, assumptions and too much calculation, doesn't consider variation in climatic condition. See, this actually is not necessarily true, because we in the MEPDG, the Mechanistic Empirical Pavement Design Guide, there are very good climatic models. There is something called enhanced integrated climatic model that actually takes, rainfall data, solar radiation, and all of that, and tries to model that. So it actually works. Mostly theoretical, we get in mathematics, maybe not be possible in real life. Maybe representative sometimes because the assumptions, yes. Predict the inelastic nonlinear response of material because we assume elastic and This is a very interesting question. This is the current practice, what we talked about, right? Does not mean we cannot do it, right? That it is possible. People have done complex models analysis using plasticity theory and stuff. It is prohibitively expensive computationally. It takes a lot of time, but still can be done. It's not practical. Yes, I agree. Possible. Yes, possible. Actual field condition, response performance, blah blah blah, reliability issues, maybe how to incorporate reliability, I guess. Yeah, the inhomogeneous and stuff like that might vary in field scenario. Okay, mostly pretty good. So I think we are all on the same page. Couple of more things I want to cover before we can break for lunch. This is the overall model. This graph is from the paper I will give you during lunch. So you will see this. Inputs, you saw that material, traffic, climate, all of that go into the structural model, which is what your IIT PAVE is, your layered elastic analysis. You can do anything, right? That your finite element model, whatever you do, pavement response, sigma, epsilon, delta. Then you go into transfer functions. That's the most important part. Transfer functions. How do you develop them? What is the relationship? What are the factors? Because if you go into the old asphalt institute method and stuff like that, it's actually, it just says number cycles to equal to a function of tensile strain at the bottom of the asphalt layer. It's a fourth power or something like that. It's that simple. You can still do it if you're doing like a, just a regular rural road design or something, quick design. You can do that, no problem at all. But things are not as isolated, so that is the reason mechanistic empirical pavement design considers many things, and then distress performance, and then design reliability and design iterations. So this is the reason at the very beginning today I said something about we should know the difference between design and analysis and performance prediction. Mechanistic empirical pavement design is analysis and performance prediction, because you are selecting a section. You are not starting from scratch and the system is not saying, okay, use 8 inches of aggregate, use this many inches of asphalt. You are saying, what if I use this asphalt, this much, this much, this much. You test it, it works or does not work. You have some standard service performance standards. It either works, does not work. If it doesn't work, you reiterate, right? So that is the reason I personally, I've seen, I don't remember who I learned this from, but whenever I write, I don't call mechanistic empirical pavement design, I actually call it mechanistic empirical pavement analysis and performance prediction, because that is what it is. You analyze, you predict, and then you reiterate. That's how you optimize the design. Okay, the very last thing, it's actually, this is another way of the same graph, and it talks about pavement smoothness here, and you can set failure criteria and design reliability and here. Okay, the very last thing we need to do is, I haven't talked about the levels of input in mechanistic empirical pavement design. Okay, again, this is going to be a little relevant when we go into other blocks. So there are actually 3 levels. So level 1, 2, and 3 of material inputs. Okay, what are material inputs? Okay, maybe it will take more than 10 minutes. How do you test the construction of a subgrade on a roadway in the field? Who has worked in the field or any internship? How do you test it? Density. Very good answer. Anything else you do? Do you do CBR in the field? So don't say research answers. Density is the only one I know of right now. You know. DCP do it in a right. If I ask you to give me an equation relating density with elastic modulus or shear strength or anything, can you do that? Is there any physics that links density to modulus or strength? The answer is no. You can do empirical, you can say this is my density, this is my thing, this is what the relationship I have. That's different. It's not physics. There is no physics. There is no mechanistic relationship, right? So in mechanistic empirical pavement design guide for subgrade soils, aggregate bases and stuff, density is not a direct input into your mechanics. What is a direct input is your modulus and your Poisson's ratio, right? Those are the two things. So the level of input in a mechanistic empirical pavement design guide, there is level 1, 2, 3. One is you are in a purely research environment and stuff where you have tested everything for what you are trying to do. Like let's just say tomorrow IIT Bhubaneswar is going to construct a pavement test track. So now you are trying to characterize the material to construct it. So you bring the soil, you do all the classifications, you do all the shear strength testing, the resilient modulus testing, all the inputs go directly into your mechanistic analysis procedure. That's called level. Okay. Level 2 is you have some information, but you don't have everything. Let's just say the resilient modulus test device breaks down, you can't run it. But what do? You probably are able to run CBR, you're probably able to run DCP, you're able to do something, right? And then you use what is known as these correlation equations to predict from CBR to resilient modulus, to DCP, to CBR, to resilient modulus, to R value, to resilient modulus, to from density to, I mean, something, you're doing something. That's called level 2. Level 3 is when you don't know anything. Now you're just talking about a soil survey report and say, okay, for the district of Khordha, this is the soil type that is there for this kind of a soil. It's a medium plasticity clay or something, or low plasticity clay. For a CL material, a representative modulus value is 15,000 psi, something like that. That's called level 3, right? So you as a engineer will have to decide for what material, what property, what level you have and stuff like that. The unfortunate part is that in the current version of mechanistic empirical pavement design guide, aggregates and soils level 1 input does not exist, because stress dependency of resilient modulus is actually not directly considered. It is just assuming a constant modulus value. On the other hand, for asphalt and for concrete and stuff, you can actually put level 1 inputs and stuff, right? So the way the system is designed is how much confidence you have in your data, level 1, level 2 and level 3. So just keep that in mind, that what level of information you have, and based on that you can do your design and stuff like, or analysis and stuff like that. And then comes the whole concept of global calibration factors versus local calibration factors. What is global calibration factor, local? What global calibration factor is, this much horizontal strain, this much vertical stress, this is blah blah blah, that actually leads to this much fatigue cracking on an average when I use the national level data to calibrate and stuff. Whereas now you are in the state of, because I live in the US, in the state of Oklahoma versus you are in the state of Arizona versus you are in the state of Illinois, the soils are different and everything. So now you have to take your own traffic condition, your own soil condition, your own climatic data, and then you are now going to say, and you are going to observe a pavement, saying that this is my pavement that is constructed, I am going to observe it, I am going to monitor its performance, and then I am going to map that, and that is where you are going to do what is known as a shift factor. That shift factor is basically the local calibration. You go from global to local, right? That is how all the equations are developed and stuff. And the problem with local calibration is it is extremely effort intensive, money intensive, and it is extremely strategic. Like for example, a DOT will have to make a plan and go accordingly and stuff like that. If in the middle the DOT engineer leaves or something like that, then things fall apart and stuff like that, right? So that's basically the framework of mechanistic empirical pavement design. So I think that's pretty much it what I have for you today before the tutorial. For the tutorial, it's going to be, I'll just give you a paper, you're going to read, and you're going to just start building an Excel sheet. It may not happen today, you may have to do it at home or do it another day or something. We'll see how much we can do, we'll discuss a little bit about it. But yeah, over the lunch I'm going to send you that paper and maybe another handout, and then yeah, let's break for lunch, we'll reconvene after that for the tutorial. Okay, right. Thanks folks.